Alright, hello everybody, how goes it? Big moment happened yesterday. We finally got the scripting language working. But to kind of show off what's going on here, since I didn't actually show a recording in the Discord, I just posted a screenshot. Trust me bro, it's working. But no, it is actually working. You can see the second half of that function's there. I edited the debug output of the intermediate representation so it actually shows which operation is which, because these variables here on the intermediate representation are which previous operation's value it's using. So it is like a SSA form graph basically, but pretending to be a register-based virtual machine. Resorting to dark rituals now to help you make it in time for AWE. I think I'm actually giving up on the AWE thing. I would probably legitimately nearly kill myself trying to actually make it to that deadline, especially with other work. So the much significantly more flexible deadline I'm putting on myself is Stanford's hackathon in November. I think that is that's far enough off that I can see myself actually reaching that deadline now, especially with all the Rust rewrite stuff I'm doing. Which, to be fair, the Rust rewrite for Brane script is already done. That's fully done. We're further along in Rust than we ever were in C++. So that's good. But yeah, here's the LLVM intermediate representation that we generate from the bitcode. So here's the Brane script IR, and then this gets turned into actual instructions. And the reason why there's significantly more LLVM instructions is because anytime we do a load operation, this takes in a 32-bit integer, and then behind the scenes, that 32-bit integer is split into two portions. We shift it right to get the binding index, and then we do an AND operation to get the lower 16 bits to get the memory offset or index, and then we do a get element pointer to get the actual index of the memory to access, a load operation to actually get the pointer to that memory that we're accessing, and then we do another get element pointer to then shift our pointer to the actual spot in memory that integer wanted. So accessing an integer pointer in Brane script does it takes that many operations. Looking dangerously close to straight up assembly there. It is. No, that's exactly what it is. This is LLVM intermediate representation. LLVM is a compiler backend. This is a compiler. So this is a unholy amalgamation between WebAssembly, which is assembly code, and SSA format, which is kind of register-based stack machine where you can't ever assign to a variable multiple times. There's no actual registers here. I let the actual JIT runtime do register allocation, but it's assembly code without registers. It's assembly code operations. It gets compiled down to actual assembly code, and then actual machine code. Here, let me actually just show what main looks like. These two lines here are where we grab our functions from the runtime, and those functions are completely JIT compiled. They're now machine code that we get a actual function pointer to. There's no interpreter. There is kind of a runtime that manages the memory for those, but there's not a runtime in the sense of a garbage collector or anything. We're going to be writing a runtime, but the actual functions themselves aren't run by anything other than the CPU. This is straight up machine code. Then we create a stack page. So this is all the memory that we're going to give the scripts access to. I'm doing the WebAssembly thing where scripts don't have any access to any memory, not even the stack. I tried doing the stack. It was just hard to let them access dynamically allocated memory and the stack at the same time. So I'm like, okay, we'll just do what WASM does and have them use the same memory system. So it's as fast as a regular stack. It's just allocated behind the scenes in heap memory. In this case, it might actually be on the stack since this is a statically allocated vector or slice. But anyway, we have a stack page and then we have a bindings page, and this bindings page is the list of every single memory page that the script can access. And right now it's like uint16 max. Since we're already doing an AND operation, we can change the size of this binding page at will. 65,535 is the maximum value of memories that could be bound to this. We can also dynamically swap those out as well. Then I allocate one argument struct. Technically there's a couple. If we're referencing our example script here, this is what we're actually compiling. So the first argument is like start, add, and add 2. Basically we're just doing 2 addition operations. And then this one, what it returns is the result of the add and then the other operand to be added. I'm kind of templating out an async pipeline. There's no reason for this to be asynchronous because it's just 2 add operations. So yeah, we pass the added value and the next value to add to the next stage in the pipeline, or at least that's what the grammar is representing. Behind the scenes, these little parentheses, this is like an anonymous struct, and that's constructed as a struct on the stack. Technically, we should be able to optimize that out if we wrote an actual optimizing compiler, or we run LLVM optimizations after the fact. That's something we'll have to look into later. Then the second stack takes second pipeline stage takes the result of the last stage that was passed here, and then does another add operation, and then we call next stage again with the result of that, and that's what returns. And it could be next stage, it could be break. I haven't really fully decided on what I'm calling these flow control function. Showing what that looks like from the caller side, I made an arbitrary stack offset because we can tell the actual function signature that we're calling from the runtime side of things is, where is it? If I go here to the functions and then JIT function handle, it's right here. So it's a raw function that takes in a pointer to an array of bytes, and that's like our bindings list, and then the actual memory bindings. So this is the memory we want this function to operate on. But then the other thing we pass into is the pointer to the start of our stack frame. So this is the stack pointer, and the script itself isn't able to actually change this. That's all handled by the JIT runtime. When it compiles the structure, the intermediate representation can't access this, but it's compiled in such a way that it does affect that. This is just a pointer to our input struct. So we do pass input through the stack. We have this arg struct that can represent all of our input and output values. And then here I just grab a reference to somewhere in that first memory page. I have the stack pointer arbitrary offset. We set the arguments to 5, 3, and 11 respectively. Print out that debug stack, and I was lazy, so we just do new lines with print statements. And then here's where we call the first function, and we just pass in the bindings page as a pointer. So this is a pointer to a list of pointers, and then we also pass in our stack pointer, which is a 32-bit integer with the high set of bits representing the memory page and the low set of bits representing the offset within that memory page. So you can add and subtract to that the same way you would do a regular pointer, and it will add and subtract within the memory page that it's bound to, and then if you add too much, you jump to another memory binding, which is behavior that we should guard against at some point with like debug assertions. But then after returning, we print out that arg struct again, overwrites the input struct with the output struct. So there's like that implicit, before you call any function, if you don't want to affect the structure that you pass in, you do allocate some memory and then pass it in. But that's all handled by the runtime. You don't need to worry about that as the coder yourself. And then we just pass the same thing that we passed the first one, because we want to pass this to the next state. We do another add operation, and then we get the actual results. And yeah, that's what we have so far. The only operators that are actually implemented are the add operators themselves. We don't have implicit function arguments because this is secretly also a struct that's getting passed into a function. So anytime you see parentheses with named arguments, all of those are implicit struct definitions. So like next state is a structure itself. Alright, to get to the actual, like, what are we doing this stream? I was just gonna take some time and flesh out the rest of the language. We're probably just gonna be a shorter stream today. So let's jump right into it. What do we want to add? Let's do a subtraction here and just implement more. I think I already implement all of the operators into the compiler itself. But then again, I did want to do signed versus unsigned and have that work properly with like division and whatnot. And I did end up deciding that I do want the intermediate representation to be more explicit rather than implicit, because I was going like the implicit route of like, if you do an add between two I32 values, then, you know, it's just implicitly like works that way. It means I don't need any like unsigned types actually in here. Technically, I do want to keep unsigned types in this because we do to the runtime report what types everything is. So we need that. But for the actual like bytecode representations, it doesn't. This is just a int32 value. Floats need to be different because they're stored in different registers. And they have a different data layout. But yeah. So remove the signed constants, or the signed variants of constants. And then for all of these, the size of the add operation doesn't necessarily matter. Most backends, maybe crane lift is different. I should probably check what crane lift, how crane lift works, because there's a very good chance that I will write a crane lift backend for this to complement the LLVM backend. So if I can see a world where on standalone headsets you use the crane lift backend because the compilation pipeline would be significantly more efficient. On PC you use LLVM, where there is a much higher initial cost to loading scripts, but then the scripts themselves are faster, meaning like PCs would have more headroom to do more cool stuff. Let's see what their IR looks like. Oh, it looks very similar to LLVM IR. It is SSA form as well, I could tell. Has all the same integer types as I was targeting. It can only represent F32 and F64 types. LLVM is able to represent 16-bit floats, but this looks like it isn't. So I'm fine with my like only having 32-bit floats in here. 16-bit floats, I think they're like faster for GPUs to compute, because one of the things you have to worry about on the GPU is the amount of data you can pipeline through things. They do support SIMD vector types. I wonder, do they have a builder? And do they have a crate? Okay, good. I don't have to clone the entire WASM repository. So let's see the dependencies. So there's the code generator, there's the front end. So this is like a builder. Oh, interesting. They have an interpreter. There's the JIT. And then there's like caching files if you want to. I'm most interested in their front end. I desire the documentation. There it is. So I'm not really able to super take advantage of platform-specific variable optimizations, since I already have it in SSA form, unless I actually put lambda statements into my intermediate representation, or like a mutable variable type. But I think for now, just having everything on the stack is fine, mostly. But it's good to see they do have like a builder system. There's your integer add. Right, what I was going to check while I'm actually looking at this is, does the size of integers matter, or are they implicitly determining that? Because this doesn't look like a sized operation. For stuff, yes. I do like seeing all the SIMD expressions there. That means in the future I will be able to add like SIMD optimizations into both backends. They do have generic commands for stuff, and like the actual intermediate representation isn't generic, but the builder is, so I can keep like the size of the variable operation generic, like add and subtraction, those are generic. Think you will ever resort to building the firmware for a custom headset that runs this natively, like part of its OS? I don't think I need to go that far, because I've already gone far enough to make this run on stuff it's not explicitly like designed to run on. And the intermediate representation is generic enough that it's not a raw bitcode that could just be run. Like there'll always be a JIT step. So without a slight redesign of the language at this point, I guess you could ahead of time compile for a specific headset. Basically the answer is I don't think I need to get the results that I want. Like it's still going to be one of the fastest scripting languages out there with the current course that I'm going. I guess right now it already is implicitly part of the two values. I wonder how LLVM-IR represents the return values, because like if I tell it, hey, add this value to, like, add a 16-bit integer to a usize, does it return or if I say add the 16-bit integer to a 64-bit integer, does it stay a 64-bit integer in the output? Here we go. No, that's an allocation. Where's add? Here's the add I32. Okay, so it does have the type as part of the add operation. Then if I look at crane lifts IR, you can see the iAdd operation. The instruction itself is the type to add, I guess, because iAdd a pointer-sized integer representing an address. Yeah. This is adding this immediate to value 4. That's what's going on there. Very WASM or WebAssembly. This is a float division. How does it... So that's a float 64. These two values that it's dividing are float 64s. And here, v4, I'm not seeing a value of 4 anywhere. Where is this defined? I guess it just multiplies v4 by 4, even though v4 doesn't exist. Oh, wait. It's an argument to the block. Never mind. So when we jump to block 3 here, v3 gets turned into v4. That's what's going on. If I do want to represent basic blocks in the intermediate representation, I might have to do something similar to this. The point where in their kaleidoscope tutorial, they're like, yeah, just use this optimization pass, where you just upgrade stack memory to pointers. And I need the LLVMIR. Sorry, I'm going on a complete squirrel right now. Awesome devs. So the good news is we're allowing use of something other than JavaScript for WebAssembly. The bad news is it's assembly. Well, that's actually the good news, because that means you can compile whatever you want into assembly, theoretically. And there is like pretty wide support for WebAssembly compilers. Like Rust has it as a native target of their compiler, and then like Inscription is like a pretty good compiler for C++ and C. I know like I've worked on game engines where the runtime was written in C++ and then compiled into WebAssembly. We don't want that gentle introduction. We want the raw, uncensored introduction. Okay, what was it called? There's like a join. If we go to the kaleidoscope tutorial and look at control flow branching, there's basic blocks, and then you have to say that like a value could be the result of this code path or this code path. I guess we aren't doing optimization passes. Wait, are mutable variables after control flow? So code generation, optimizer support, language control flow. Yeah, mutable variables is all the way down here. Yeah, cause complexities in a single static assignment. So you can't, SSA form basically means you can only assign to a value once. Well, what if you assign to a value multiple times in a loop? Or if there's an if statement where there's like one possible value here and one possible value here, and you need to define both of those in the graph, so they have different value names, but you need to use one or the other. How do you represent that? It's called a phi node. It's not called lambda, it's called phi. In condition true, we have this value, and in condition false, we have this value. And then we need phi, where from that label, we get this one, and from this label, we get this one. However, SSA construction requires non-trivial algorithms and data structures. It is inconvenient and wasteful for every front end to have to reproduce this logic. And the trick is they literally tell us to use analysis passes, which convert stuff on the stack to stuff on the heap. The problem is that the way that I handle my language is everything is not on the stack, it's on a virtual stack. So I don't think this optimization pass will work. I'll have to actually learn the non-SSA system for that. But that's for when we implement control flow, which we're not doing yet. But it's just like the seeing the block having input here was interesting. So yeah, this is a full I64, and then we're adding, I guess, an immediate value. Yeah, even in here, both of these are 64 bits, so this add command is like fully generic even in their intermediate representation. Many instructions are polymorphic. They can operate on different types. Of these types, I32 and I64 are the most heavily tested because of their use by WASM time. There are no known bugs in I8 and I16 and I128, but their use may not be supported by all instructions in all backends. That is, they may cause the compiler to crash during code generation with an error that an instruction is unsupported. That will be fun. There are no known bugs. We're not going to say there are no bugs. We all know that would be a lie. We just don't know what they are. Yep, so when my runtime, crane lift runtime is blowing up, I'll have to spam pull requests. This instruction does not depend on signed, unsigned implementation of the operands, and doesn't care about types either. Nor does it return any errors either. It just goes, okay, maybe when we do the final build command, it actually validates everything. I am just very concerned on like the addition side of things. I guess I could just, for now, take the Rust route of literally forcing both arguments to be the same, which is what I'm currently doing. And then I'll follow the trend of doing like, there's signed multiples and unsigned multiples. Remainder is also like a division operation. Yeah, unsigned and signed remainder. And I think the rest of those make sense. So now we have our actual signed types. Let's go to the compile. And now we need to, inside of compile binary operator, when we implement traits, that's when we'll need to put in the ability for us to override operators with traits. I like this. We will use the left type as the type. So then in the future, when we're figuring out like operator overrides, it's like the left types overrides to access stuff. Now we know that all of these are for native types only, and we can keep the logic that way. And since for the moment we want to enforce that they are the same type, then for struct, we also want to bail. Oh, wait. I don't want to bail for native. We want to bail for struct. There we go. So now we have both native types. And we'll say if L type is not equal to R type, then we want to also bail that type and that type, which is left type R. We used to have a little bit of indication of what's going on there. And now I know for a fact this will return correctly. Instead of ops type here, we're going to do L type add sub mul div. Do I want to do unsigned add? Do I want this writer class to take care of signedness? Since I'm passing in the type, I might as well also handle signedness. So we will copy this function, paste it 3 more times. Actually, we need to paste it 4 times because we're doing remainder as well. So I'll just, so this is addition to ir op tract, and that works fine that way. And for multiplication, we do need to match. Do I want the type as part of it too? I think I do. If I look at the runtime, it just takes an integer, and that's the same thing the other runtime takes as well. So I only really need to do int versus float versus vector. So add I, add f, subtract integer, subtract float, and then here for signed and unsigned multiplication, it's actually super easy because we only need to add 1 more here because floats have their own way of handling signedness, which is always being signed. And then there's no such thing as a remainder function for floats, I believe. Integer type, integer type. There's float compare, float compare. Oh, interesting. You can do bitewise ORs on floating points too. I guess that just happens in, I think it's the XMM registers. Floating point comparison. There we go. Float add. Yeah, it just goes straight to like a square root and multiply and add. Interesting that that has to be an instruction itself. Float, multiply, and add. Yes, do I want to implement, I'm gonna add compare to the name of that, just so it's a little bit clearer that those are comparison operations, but we can get back to that later. So let's add all of our addition stuff. Where was, I like squirreled right in the middle of adding these. So multiplication, division, and remainders. Maybe I copied these too soon, because now we actually do need to match on the type. This is going to be the unsigned add integer. So is this add you add I? Was that how I did it? No. Right, because adding isn't signed. It's just integer versus float. We'll implement the float as well. There we go, and I am definitely copying this and renaming it for doing subtractions and all of the other functions. We'll do subtraction first, so subtraction integer, subtraction float, and then multiplication is fun because we have to do signed versus unsigned. Let's organize these by signedness. So there's all of our unsigned theirs together. Not, you know, organized, which I would like them to be, but there's all of our unsigned values. Let's copy this expression, and then need to rename this to multiply. Oh, no, I just called it smol, umol. So these are implicitly integer, right? Wait, not and, we want float add. How long do you think your project as a whole will take to complete? One, it's never going to be done, but like the real question is, when will it actually be usable to make projects with? And my like current deadline I have for myself for like being able to hackathon with it is I'm gonna try to make it to Stanford's XR hackathon happening in November. So that's like my target deadline for having something working and usable. For like actual projects, probably like a couple years. And like with coding, you can't really do specific deadlines because you just straight up don't know how long things are gonna take. The longer you code, the less you like know how long things are going to take, unless it's something you can literally do instantly. The answer is I'll have that done in an hour, or I will have that done in 2 months, and depending on specific bug and how hard it is to fix specific bug. Let me just change this to div5. Finally, we get to do remainders, and for remainders, we just want to throw an error that can't get the remainder of floating types. So we don't need to do any extra stuff. All right, so now the intermediate representation will be outputted. Now we need to actually implement it in the back end. Is that another Outer Wilds world? No, this is a world called, let me get it right. It's called Blackfire. It won some awards, and it is a really beautiful world just throughout the end. It won like art direction awards because it is very artistic. Game of Fire isn't black? Okay, it's like the closest you can get. That's like how a black light is that color, like UV light. So lots of like different enum casting stuff. In addition, on the assembly language side, there is no signedness. Your compiler doesn't know what signed versus unsigned types are. There's only signed versus unsigned operations. And in the case of add operations, because of how integer types are stored on the CPU, for addition and subtraction, it doesn't matter what signed variables are. It does for multiplication, division, and remainder operations, but for addition and subtraction, like the overflowing of an int, like, well, yeah, that's just how integers work. Like halfway through a signed integer, where like an unsigned integer would just keep going up, an unsigned integer, the middle value is the negative max value. And then like as you like continue adding up, the negative number goes down until like at the max value of an unsigned, it's also the -1. So when you add numbers together, signed or unsigned, that mathematical property makes them just work Like, you can add them both interchangeably and it just works. And overflows work exactly how you'd expect them to. You're not getting me with that. But this project was C++, and then I rewrote it in Rust. I did the meme. It only took me a week. Then I'm just going to nuke every single other one of these, and then re-implement them. Then this isn't build int add, this is build float add. Just realized if I'm going like explicit for all of the different things, would I have to do that for the compare operation? I mean, that's what WebAssembly does. Rusty wasm. No, it's its own thing, with its own innovations, like not needing to allocate 4 GB of RAM for their security concerns. Okay, that looks all implemented. Next we do multiplication. Do you prefer Rust to C++, or what was your reason for switching? Greatly prefer Rust, especially when you're dealing with walking trees, which is the majority of what I'm doing. Like, just the match statement alone makes it worth the switch. One singular grammar concept. Is it only division and remainder that require signed versus unsigned? Your pressure probably has something to do with it too. No, I am an entirely independent thinker. People could never pressure me into switching languages. And if they did, that probably wouldn't be recorded on stream at some point. I guess, yeah, with multiplication it wouldn't matter. I remember when I was learning assembly, there was other stuff to do with it. Yeah, it's signed and it's only division that's signed versus unsigned. Only division. Well, I guess I am undoing the many changes I did to... Guess we go to int multiplication and then that, but we can keep the rest of it the same. You really need unsigned? Yes. I like unsigned variables. Have you ever had, like, a score in a game go negative? That's because they didn't use unsigned variables, and it's a very strong pet peeve of mine. If a val is greater than 0, val equals 0? No, what? What? No. Unsigns are good because they can store twice a higher number than the signed versions, because they use all the space that would be used to store negative values for storing higher positive values. And why would I add an if statement? That's extra computation. No. And also, your UI would still be glitching and not showing you the correct store. Add another long? You run out of them eventually. And also, what's this, like, calling variables long? How long is a long? That's very vague. Just give me, like, I32 versus U32 versus 64. I want to know how big my variable actually is. Well, I know how long... I know what the variables are. Like, I spent enough time in C++ to know. But that's the thing, it's implicit. There's a learning curve to that. I want the language to not hide things as much as possible. Or at least make it feel like it's not hiding things. The parts of it that you use, the things that you use aren't obfuscated. Programming is an interesting thing because you get very Stockholm syndromed into all of the foot guns that you've learned. Like, I was talking to an Unreal dev recently, and they're like, they love Unreal because of how much more reliable the physics system in Unreal is than in Unity, like, fresh out of the box. And, like, I have done a ton of physics stuff in Unity. For every single thing he said doesn't work in Unity, I know the workaround to how to get it to work in Unity. But what was interesting about the conversation was it made me realize, like, every time it was like, oh, you just have to know this thing. Oh, you can do that, you just have to know this thing. But in Unreal, you don't need to know something, it just works. And that made me realize, I need to make sure I'm careful not to put, like, the same foot guns into, like, the stuff I build because I'm conditioned to them. Like, I need to make it intuitive to, like, when you could make something in such a way that people wouldn't have to read the documentation for it, you should probably do it that way, as long as it, like, doesn't significantly hamper performance and whatnot. What are your opinions on using AI for coding? Do it as long as it doesn't hamper the quality of your work. It's free, it's a tool there that you can use, as long as you aren't sabotaging yourself by doing it. Use the advantages you can get. If you are trying to learn, though, don't use AI. It will significantly hamper your ability to retain what you've actually coded. So while you're trying to make like a map, like mental map of how something works, having something else do the work of mapping it out for you will sabotage that for you. So if you're building something and you don't care about learning, use AI. And if you already know how to do what you're doing, like, please make Brane engine have deterministic physics. Oh yeah, of course. Like, I'm trying to do networking. Like, network physics, of course, is going to be deterministic. This is how many R's are in strawberry. True. I've heard that Claude builds an entire JavaScript web page to count it for you, if you ask it that. Haven't tested it myself. So now we need to do division. So it's like SDiv. LLMs see individual letters and words. They see tokens, which are chunks of words. So can't actually count it. This is going to be fdiv, and then this is going to be sdiv int signed divide. Then I'm going to copy these for remainder. What is the S prefix? Signed. Signed versus unsigned. So use unsigned, S is signed, F is float, obviously, and then in the case of both signed and unsigned being handled by the same case, I just do I for integer. So I think that fully implements basically all of those operators. No sign, unsigned for floats. Floats are only signed. They can only be signed. Though when you compare them, they set unsigned flags for comparisons, which is luckily something I don't have to worry about because every JIT runtime extracts over all of that madness. At least on x86 registers, they do unsigned flags for the signed floating point variables. I wonder how that happened. Did I just do some operation that deleted every 8 in the file accidentally or something? I guess U32 was the only constant I was using, and that was the one that I deleted. Or rather, only constant that I had implemented. I guess I did do some operation that deleted every 8 in the file. Is the whole engine going to be rewritten in Rust, or only the scripting engine? At this point, probably the whole engine, because I've already been doing like a full engine rewrite. So at this point, it kind of makes sense to like just continue the rewrite in another language. In fact, the reason why I stopped working on it and went over to the scripting language is because there were language features in Rust that I wanted to be using for like all the serializer stuff. And I thought, hey, I'll just finish my scripting language, put those features in there, and that way I'm like not just jumping ship to Rust. But now, of course, I actually am using Rust for stuff. So either I still like the idea of writing engine UI stuff, rewriting that in the scripting language itself, which is something we still might do now that I have the longer Stanford deadline. Like, I just think that makes sense. Like, use the engine to build the engine. It also would make concurrency easier, because I do want to do a lot of concurrency stuff even in the editor itself. Good developer experience. The editor is actually fast, even though it's a dev tool. What? But yes, I probably am rewriting the core engine stuff in Rust as well. I'm going to write as much of it in the scripting language as possible, because the scripting language is going to be fast. Might as well use the scripting language for as much as possible. In the same way that a lot of Unity's UI is written in C#, for better or for worse. Mostly for better. Mostly for better. Do I have any other things to figure out? Yes, I do. Not compile Brane script compiler, and assertion fired. When we, not yet implemented. What is not yet implemented? Brane script looks kind of like Rust. Is it also similar in functionality? I'm planning to do a ton of stuff very similar to Rust in the language. I don't know if I'm going to implement a borrow checker, mainly because I think that would be... I don't want to scare off all the game devs. I might do like add one in later as an optional option you can toggle. But for like everything else, like traits, definitely doing traits, doing enum based checking. I don't know how long it will be till I get match statements in. I very much would like to do match statements. I guess under the hood I could just implement them as giant if-else blocks, which is kind of what they are. Jumped tables, I can implement jump tables in certain cases, but that would be dependent on optimization mostly. In the bit code, I guess that would just be a switch statement. But for everything but the borrow checker, it will be kind of like a reskin of Rust, but with a lot of concurrency stuff added in. Abstractions over concurrency and like asynchronous and threading stuff. What these square brackets are? So that's because this isn't a function, this is a pipeline. So the square brackets are kind of like a way to say every like little function body looking thing defined in here is a pipeline stage. The way that we abstract concurrency is every single one of these pipeline stages are bits of code that can run without there being any break in execution. Like, I don't want to do an async keyword. I feel like an async keyword abstracts over too much. It makes it a little bit unclear about like when the breaks in the program are happening. You're basically pretending that this is when you use the async keyword, you're pretending that your program is single-threaded. And I don't want to pretend the program is single-threaded. I wanted to make it easy to do multi-threaded stuff. So the way the pipelines work is every single one of these stages can operate completely synchronously. Like, they don't ever need to wait on any information. They just run and then they finish. And then to the next stage, they can pass values that the next stage will need to wait on. So I have like this dependencies field, where if I spawn any other pipelines inside of this pipeline stage, I can say, hey, wait until those pipelines are done before running. Or wait until these values. So this is where you'd usually put an async keyword. Instead, you pass multiple values in, so it incentivizes coders to wait on multiple things at once instead of waiting on one thing at a time. Make the most efficient thing the easiest thing to do. So this next stage call moves us to this stage here. I'm not actually showing off any actual concurrency here, because there isn't anything to actually wait on, since this is the simplest case possible that still has pipeline stages. But yeah, so this runs and then this runs. And if there was any like asynchronous things to wait on, they would happen here. Like, let's say we did a network request, like API address, and we did this, and then we passed this into here, like fetch res is equal to fetch, and then I could put inside of here, we need fetch res, which is like a HTTP get result. And this is all like pseudocode right now, because none of this is actually implemented. And then by the time this pipeline stage runs, this fetch result will be like fully resolved. So you won't ever have to do mutex lock, for instance. It'll be impossible, as impossible as possible, to completely prevent mutex deadlocks and similar things. You just go do all my stuff to request information, and then next stage, you do all of the stuff with that information, request the next bit of information you need, and then continue on. Kind of this request, use cycle. Keep using my threads manually, thank you. I mean, to each their own. Do you actually write, like, heavily multi-threaded things, though? Or do you write very loosely multi-threaded things where you try to avoid as much multi-threading as possible? Because, like, that's what I do outside of, like, async Rust with automatic, like, the Tokyo runtime, which I don't want to use because it feels too abstracted. And, like, I ran into so many mutex deadlocks with that system. Try to write my code so it works maybe, and try to add multi-threading where it's maybe, but probably not needed, and where it's needed, I make an educated guess that it's not needed. So basically, the reason why I'm writing Brane script like this is because I just want all the threads being used, and I want people not have to worry about, like, should this code be multi-threaded, should it not be multi-threaded? Just let the runtime decide. And then everything's written in such a way that it's not an absolute pain to then change stuff to be multi-threaded. You just have to go, oh, my code is already multi-threaded. Maybe I needed to change like the actual algorithms themselves so like the stages are more efficient. But it's like, by performance by default is my philosophy here. Let me do a ton of work so you guys don't have to. Maybe you'll have to learn some things, but you won't have to do work. Let's see, I'm gonna reference my old version of the last push I did to Brane script. Build int add line 32 pointer stack offset. Okay, this is the compiler. No, runtime. This is the runtime. That was my old implementation of this that I had deleted. See, that makes starting threads easy, but it doesn't make communicating between threads easy. Like, I can do spawn a new thread all day. That's easy. What's hard is having a spawn thread, having it talk to another thread, and like, what you're describing is a thread pool, which is like the step above raw spawn thread, where it's like, oh, spawning a thread takes time. Let's just have a pool of them. Virtualize it. Int from string is the thing that they do for... Just create a global variable referenced in both threads when I need them to communicate. Do you at least throw a mutex on there? There's like so many concerns that go into getting multi-threading working well that I do not want to have to teach game programmers how to use. Alluvium const int of arbitrary precision. Then this is how many bytes it is, but it calls it words. Wait, isn't a word 2 bytes? I usually program in Python. Okay, Python is probably saving you, even though there are mutexes and mutex locks in Python. So Python may be like, I don't know. Well, it depends on how mission critical your Python is, I guess. Is that learning a new language is already a turnoff for people moving from something like Unity, but your language is fundamentally different from differently structured than conventional languages. Yes. I was like flip-flopping, making it as similar to C# as possible, aside from just the pipelines thing, as like a let people carry over, but I'm like, do I want to, like, legitimately, possibly heavily nerf what I'm building just to help with the adoption curve? Or do I want to make something, like, that after you learn it is potentially significantly better, and a better to use long term? Like, after they use it, maybe they'll be able to fall in love with it, instead of, like begrudgingly using it like C++. Though C# is a good language in terms of the likability scale. And I'm like, I would much prefer to have a learning curve and then have people like it and have myself like it. Because I am not going for like I'm not doing a to the moon startup. I'm doing like something that I want to be sustainable over the long time and not blow up, make $1 billion. I'm a billionaire, yay, and then I just go off and do something else. No, this is like what I want to stick with for a long time. So I don't care as much about the initial adoption curve. Like, it's important, the onboarding experience is very important, but I'm not going to nerf the tools to make it easier. I'm going to make the tools better, easier to use, but I'm not going to nerf them. Or make them, like, the editor will look like Unity, but it won't function like Unity. It will function better than Unity. I mean, they can do single stage pipelines, which are essentially functions. Like, what most people do, or at least what I do when I learn a language, is I go to the examples, and then I just, like, find example of thing I want to do, copy paste, see how the grammar differs from other languages I already know, and then I'm basically good to go. So at first I'll go, this is a funky looking function, because most of my examples at first are probably just going to be single stage, and they'll go, oh, this is a funky looking function, and this part here, this is going to be implicit as well, so it will just look like this. This looks very close to a Rust function. It looks exactly like a Rust function that's returning a anonymous structure. So I can just explain, since this is a language that supports a nice node graph, all function arguments need to be named so that the names show up in the node graph. Cool, they'll get that. And this is a pipeline, not a function. They'll go, yeah, okay, I get it. It looks like a function though, so it's probably a function, but we just call it a pipeline. And then you're able to get started with just this, and it looks very similar to a function, just with grammar that you're gonna have to reference. And then eventually you can add on the other stuff. What major engine is using Rust as a scripting language? The Rust ones. They aren't technically majors. Like, I heard Echo was written in Rust. So there you go, there's your AAA quality game that was written in Rust, that is in the VR space. And like I said, I'm not putting the borrow checker in there, because I think the borrow checker would dissuade too many people from using it. But then again, you even have web devs learning Rust. So even then, I don't think it's a total turnoff. I don't care about it being unfamiliar. The entire thing that I'm building is going to be unfamiliar. What matters is if it's good enough to get them to switch over, not if it's the sucky in a way that's familiar. Float sub arguments were not both float values. Float f sub. So this is a problem with the compiler. Why did I put f sub in the integer area? Let me make sure I did this for addition too, or didn't do for addition. Integer. Well, I put integer add in the float section, so let me just double check. Integer. Cool, it ran. This time we have start plus add. So the first one will be unchanged. We get 8, but then we do 3, or it should be 8 minus 11, and we get 3. That shouldn't be the way that it'd be, because I see here the stack value that gets printed out is 3. 3 minus 11, so that is incorrect. Look at the intermediate representation, what it looks like. So this is correct, because 5 plus 3 is 8. 8 minus 11. Well, 11 minus 8 is 3, so it should be 5 plus 3, which is 8, and then 11 as our outputs, so 8 and 11. 1 goes completely correct. Then 1 should be doing 8 minus 11, but it does 11 minus 8. So let me just check here, like our left and right sides. Left, oh, yeah, I did swap them. So we want left. Did I swap all of them? And this, my friends, is why I'm going to write very extensive test cases before telling anybody to use the language, because I can't trust myself to not be stupid. Okay, this is now -3. That is correct. That is what we wanted to be. Subtraction is now implemented. What if I do multiplication? So you admit you're being lazy. Yes, by making an entire scripting language, I am being lazy. Okay, 8 times 11 is indeed 88, so that is working. Let's do division. 8 divided by 11 is indeed 0 if you're doing integers. Let me swap this around so it's add 2 minus value, or divided by value, and it should be at least 1, because integer division rounds down. Yippee, it is working. We now have basic math operators. The math works. When will math get implemented? I'll give that a 6-month time horizon. Now the error messages are correct. What was I gonna do? Right. Get stuff. Okay, I haven't committed anything. Imagine a world where drug dealers only give you drugs if you have an illegal prescription. That would be funny. It's like a thing being like, ah, yes, I know this guy's good for it. Hopefully you figure out how to use Git. See, the thing is, I want to switch to main, but I need to pull main before being able to switch to main without... Actually, that might have just done it. But, NVim nuked itself, as it's been doing recently. It is working. Yeah, it's working. So we added native type operators. So we can do additions, subtractions. We can even do modulus. Let me test out modulus. So we'll do 11 mod 8. That's the remainder command. There it is. That shouldn't be how that works, right? Wait a second. I made it be an unsigned remainder, which I don't think matters for positive values, but maybe it does. I'm glad I checked that. It's still saying 11. Oh, wait, what's this? It looks like a floating point remainder. It is a floating point remainder. What? Right as I was about to sign off the stream, I get another rabbit hole. That's okay, I can go till 6. We'll get remainder working. But if I do build float... Yeah, there's a float remainder. Why did I just assume there wasn't? Well, it's because in other languages, the modulus operator hasn't worked. As expected, but I guess, like it exists. The float remainder! The float modulus is real! But I do need to figure out why remainder isn't working at all. Modulus, mod. Why mod, no mod? I do rem here. Instead of doing this, we want to add in another right. Let's implement float rem libm's fmod for some targets and using the instruction may thus require linking to libm. Oh. That's not great. So it means it might not always be supported. So I may have just wasted the effort of adding it in there. I mean, I can just implement it on the runtime side if it isn't implemented. If that ever comes up, this is something that I very much like, would be able to have a native modulus operator on floats. So I'm gonna keep it and then just deal with it, implementation side, abstract over it. Here, let me check the, so this would be srem, and I do have it as srem in the print output, but I don't see srem in there. Subtraction, division, no modulus. It's just straight up not implemented. What order of operations would the modulus be? I could put it in the same section as division. I think it makes sense for it to be in the same section as division. And in here, when we do binary expression, am I not doing precedence for these? Oh, that's scary. So we'll add mod in there. For, we'll just put it in division, or in the same precedence as these for now. Okay, that generated without complaint. So we will commit this, then this will be add the modulus operator. Now would also be a good time to add bit shift operators, but I'm too lazy to do that. Doing it this way is nice because that means if people want to pull these commits for whatever reason, the compiled like parser will always match. Now we can go back to the compiler and it will complain that this case is not handled. And I'm going to badly spell it because Rust won't let me call it mod because it's looking for mod as a keyword. We'll call this binary operator mod. That is the correct value to return. Let's go. How long Nimsoni spent on his back and stuff, knowing before it really started getting the viewers from showing it off and stuff? I don't know. Because, like, his content was, like, super polished from, like, before I was even watching. His content is definitely more polished than mine, that's for sure. I need to up my game. A lot. Wait a second. It's because I'm doing... This value here is 8. 24 is divisible by 8, so it's working. 0 is what you would get when you mod that. Yeah. And then, yeah, if you swap them around, still 8. Okay. I'm gonna do that. Go back to main rs and choose something that isn't divisible by 8. Let's do, like, let's do 6 instead of 24. Because this needs to be the smaller number, and I was thinking it needed to be the bigger number because I'm dumb and don't understand how my own language works. Or math. I don't know math. I need to know math. There we go. That is clear evidence that it is in fact working. Because 8 modulus 6 is in fact 2. There we go. Now that I actually got the example put together correctly, it is actually working. Like, as it's supposed to be working. There we go. Add mod operator, and we don't have to do any weird math stuff because I was just dumb. And it was working as intended the entire time. Just need to add the parser. There we go. I'm going to sign off for the day, and we'll be back at it at some point this week. Maybe tomorrow. We'll see. Yeah, it will just... I'm not sure how much time I'll have now that I'm like actually like fully starting my studio job. Like, I'm still getting work done off stream, but it's in like smaller increments here and there, as opposed to like, here's my chunk of time where I can do a 5-hour stream. So yeah, hopefully this was fun, and thank you guys for sticking around. See ya.